So we're about to get started with our meeting. I'm really excited to introduce this upcoming talk. So we were originally going to give this talk at Perkins for Women's History Month. And this talk has been a lot of fun to work on because I'm a part of the first ever all-woman graduate class at the Ohio State University's Department of Astronomy. And so my classmates and I all got together and decided that we were going to talk about our favorite astronomers. And aside from talking about our favorite women astronomers who inspired us along the way, we also wanted to highlight each other because we're all actively taking a role in the astronomy world. And the women that came before us had opened the doors for us, and we're trying to push those doors open a little farther for the people that come after us. So it's a really exciting time, and we had a lot of fun putting together this talk. I'm really excited to share it with everyone. So this talk consists of 11 transitions. We talk about over 12 women astronomers. There might be some changes in volume due to the fact that we're recording it instead of handing off on the Perkins Observatory stage. So please be patient with any technical difficulties and any little bits of awkwardness that might arise. All right, so with that, I'm going to start the presentation.
Caprice Phillips was born and raised in Hot Springs, Arkansas, a city that lies within Hot Springs National Park, which is famous for the naturally occurring geothermal springs and historic bathhouses downtown. Funny enough, her interest in astronomy came from long drives to her grandparents' house in rural Arkansas. Caprice was fascinated by the moon and stars she saw in those drives, and it was her mother that encouraged her to pursue her interest, something that she is thankful for to this day. Whenever possible, her mother would let her watch astronomy shows on the Science Channel, and she got Caprice her first telescope. Since her time as an undergraduate, Caprice has had an interest in science education and outreach. During the course of her undergraduate career, Caprice pursued many science education opportunities. Her first experience came from being selected as an intern through the Shepherd Internship Program. Through the Shepherd Program, Caprice traveled to New York City to work with Code Interactive, an organization dedicated to equip underserved youth with computer science skills. With Code Interactive, she worked with students on a 14-day hiking and canoeing trip, as well as helping the students develop their own apps. One of the most memorable moments for Caprice came when she led an interactive night sky tour with the students. It's very special to her because it was the first time that she and the students had seen the Milky Way. Along with pursuing science education opportunities throughout the summer, Caprice worked as an educator for 2 years at a science museum in Little Rock, Arkansas, called the Museum of Discovery. Caprice loved guiding children through building gadgets, seeing the creativity that the children used to solve problems, and watching as the visitors were excited as they solved problems. Her love of astronomy, nature, and education led Caprice to work in 2 national parks as a night skies assistant. At Sequoia National Park, Caprice worked to develop astronomy evening programs and pop-up activities for the remote Mineral King area of the park. While at Sleeping Bear National Lakeshore, Caprice worked with staff to prepare the park to apply to be an international dark sky park by assessing the quality of the night sky and performing light inventory. Caprice has degrees in both physics and astronomy and has worked on astronomical research ranging from meteorites to brown dwarfs. At OSU, Caprice's research focuses on exoplanets and exoplanet atmospheres. She works with Dr. Ji Wang on a research project that involves using next-wave space-based telescopes to search for signs of life on super-Earths, which are types of planets that are more massive than Earth and can possibly have atmospheres that are much different than the nitrogen and oxygen-dominated Earth atmosphere. Outside of school, Caprice enjoys trying out new recipes, attending comic book conventions, and trying her hand at new crafts. For the future, Caprice would ultimately like to work as a professor and mentor students, while continuing to pursue her love of the study of exoplanets. Alongside this work, Caprice hopes to dedicate her life to mentoring and maintaining underrepresented students in astronomy.
Thank you, Ness, for introducing me. And as Ness said, my name is Caprice, and the astronomer I will be talking about today is Barbara Williams. Today I chose to talk about Barbara Williams because she is the first Black woman to earn a doctorate in astronomy. Growing up, I knew I wanted to become an astronomer since middle school. I even wrote in my 8th grade yearbook that my future profession was going to be an astronomer. I was always excited to watch those astronomy programs on the Science Channel and to see astronomers discussing all things related to space, from black holes to exoplanets. But as I watched those shows, I was quick to notice the astronomers I saw did not look like me. It was not until I was an adult that I learned about Barbara Williams, and it changed my entire mindset. Barbara Williams majored in physics at the University of North Carolina at Greensboro, and later went on to get her master's and PhD in astronomy from the University of Maryland in 1981. That was just 39 years ago. Barbara is an accomplished astronomer, and she has many academic awards and honors. She graduated Phi Beta Kappa in physics. Phi Beta Kappa prides itself as one of America's most prestigious academic honors. In 1986, she was awarded the Outstanding Young Woman of America Award. In relation to academics, Barbara served as a research associate at the National Radio Astronomy Observatory from 1981 to 1984. And later she went on to become a summer faculty fellow at Goddard Space Flight Center in Greenbelt, Maryland. She has since retired, but she was an associate professor of physics and astronomy at the University of Delaware. Barbara's research was focused on radio observations of groups of galaxies. More specifically, she used something called the 21 centimeter line to trace hydrogen gas in galaxies, as well as map distances to galaxies. She was interested in galaxy formation and structure of galaxies. She was also interested in small groups of galaxies, as they provide astronomers with an opportunity to study the dynamical evolution of galaxies. Also, small groups of galaxies are natural laboratories that can be used to study various physical processes that allow galaxies to evolve quickly and help astronomy understand galactic interactions. Barbara laid the foundation for Black women to have a place in astronomy, but we still have a long way to go. According to a study by the American Institute of Physics, in 2016, only 3% of women who earned astronomy bachelor's degrees were Black women. And only 5% of women who earned PhDs in astronomy were Black women. As well, only 2% of Black women were faculty in PhD departments of physics and astronomy. As of 2020, there are less than 30 Black women in America who have earned their PhD in astronomy. Although those numbers are small, I remain hopeful. Barbara Williams is an accomplished astronomer who broke the barrier for Black women in astronomy and paved the way for the Black woman shown here. She is an inspiration as we continue to build on the foundation she started for us, and I am happy to have shared her story with you today. Thank you. It is my pleasure to introduce the next speaker, Anusha. Anusha was born and raised in the quiet suburbs of Beaverton, Oregon, to immigrant parents from a small state in India called Goa. Like all Oregonians, Anusha loves cats, hiking, although admittedly she's not very good at it, and consuming vegetarian food. Beaverton is a possibly unexpected hub of numerous tech corporations, and as such, Anusha grew up amid a confluence of cultures which strongly flavored all aspects of her life. In the most literal sense, she actively explores all types of cuisine, much to the misfortune of her fatal sweet tooth. More abstractly, her taste in television ranges from British period dramas to Japanese anime and Korean dramas. From a young age, Anusha's family instilled in her a deep appreciation for what are now her two greatest passions, music and science. Her growth in both of these pursuits followed remarkably parallel trajectories over time. Anusha's father, influenced by his time working in Germany, encouraged her to train in classical piano, while her mother encouraged her to pursue Hindustani classical music. This was the extent of her musical taste until college. Similarly, during this time, her scientific interests were limited to what she was exposed to by her family: computer science, the field of her father's and sister's profession, and physics, which her father enjoyed learning from documentaries as a sort of a hobby. With the intent of majoring in computer science out of practicality, but still drawn to the pure sciences, Anusha went to Caltech to pursue her undergraduate education. Her years at Caltech were filled with introspective turmoil. She simultaneously developed a musical appreciation for Bollywood, alternative rock, K-pop, and Japanese jazz, and her academic pursuits were similarly confused. Anusha ultimately majored in physics, which launched her on a journey exploring device physics, quantum computation, and finally her chosen field of astrophysics, which she had always found alluring. Though she worried about job opportunities, she realized that she was in a very lucky place to pursue astronomy. Much like her musical adventures, Anusha accumulated various research experiences. Her experiences at NASA JPL in particular helped her choose the field of exoplanets as her focus. From a technical standpoint, Anusha had developed skills and interests in optics, instrumentation, and signal processing, all of which have interesting applications in exoplanet science. She enjoys teasing out information from limited data, which is ultimately what a lot of observation astronomy boils down to. From a science standpoint, Anusha can learn and apply a lot of her interests across STEM because the field of exoplanets is possibly one of the most interdisciplinary in astronomy, drawing from classic astronomy topics like stellar evolution to information theory to even chemistry. In her work, she can even apply her hobbies like amateur electronics, and if the whole astronomy thing doesn't work out, her fallback plan is to sell irresistible jewelry made from cheap resistors. Note the shameless promotion in the top center photo. Anusha feels very fortunate to be studying hot Jupiter atmospheres under mentorship of Dr. G. Wong at OSU. In the long term, she hopes to work on instrumentation for direct imaging and characterization of exoplanets.
Thank you for the introduction, Caprice. The astronomer I will be talking about today was a scientist with intense dedication to her work, a sister of deep devotion to her siblings, and above all, a woman of great strength and perseverance. It's the 18th century, the golden age of astronomy, when discoveries were dominated by amateur astronomers. On March 16, 1750, Caroline Herschel was born in Hanover, Germany, to Anna Moritzen and Isaac Herschel. She was their 8th child and the youngest daughter of 4, of which only 2 survived beyond infancy. Herschel's father made a living as a bandmaster of the Hanoverian Foot Guards, an occupation that demanded frequent absences from home for extended periods of time. Given the era, one might envision Herschel to have been trained in etiquette and skills to prepare her for entering society as a marriageable candidate, or at least to have received a sufficient education to earn her a position as a governess in a middle-class household, as working-class women of the time commonly did. Herschel's only surviving older sister left the household to pursue the latter option when Herschel was only 5. In contrast, Herschel's mother had cause for wishing her not to know more than was necessary for being useful in the family, as Herschel will later write in an autobiography. In this autobiography, Herschel fondly remembered her father's affection, though it was limited by his infrequent presence at home, as well as his efforts to expand her education in a manner that would improve her rank in society. However, the most formal education Herschel received in her teenage years were confined to learning domestic skills like knitting and the practices of a seamstress. Herschel's mother exploited Herschel's physical shortcomings, such as her disfigured features and diminutive stature, due to contracting smallpox at age 3 and typhus at age 11, thus limiting her education. Herschel's writings in her later years suggest that her mother's actions aimed to prevent Herschel's escape from the household and effectively keep her as a maid. In the meantime, Herschel's favorite brother William was making a living as a musician in Bath, England. His dislocation is not unusual, since this is during the time when Hanover, Germany, and England were united under the reign of King George II. Caroline is now a grown woman of 21 years, and William requests the family to send Caroline to Bath to aid him as a singer for his winter concerts and oratorios. He is fully aware that Caroline did not have a formal vocal training and offered monetary compensation to his mother for the loss of Caroline's domestic help. He had recently purchased and become very captivated with the 2-volume work Optics by Cambridge professor Robert Smith. On their travel to England, William introduced his sister to the night sky and made multiple stops at opticians' shops. The musical season lasted from autumn until it climaxed at Holy Week preceding Easter, and William spent the full day occupied with rehearsals and performances. During the off-season, William subsidized all necessities for Caroline's growth as an oratorio soloist, but dedicated all of his time on his newfound obsession with astronomy and developing a telescope. For the next decade, Caroline ran their home with their brother Alexander and joined a choir, which enabled her to develop a decent profession as a soloist and choral trainer. However, as William's obsession with astronomy grew to encompass the entire household, his diminishing musical career due to neglect dragged Caroline's down with it. Fortunately, his reputation as an amateur astronomer spread to the Royal Society of London. By this point, he had developed a 6.2-inch telescope with mirrors he devotedly ground himself. Throughout the creation process, Caroline assisted him by reading novels to relieve the boredom that accompanied hours of grinding optics, and spoon-fed him meals as depicted on the left, by way of keeping him alive, as Caroline later wrote in her autobiography. With an instrument rivaling the highest quality of its time, he discovered a moving object that he originally thought to be a comet, given how much it appeared to move on the sky. This object was in fact the planet Uranus. The discovery merited an opportunity to secure patronage from King George III, allowing William to switch careers to astronomy. He became an astronomer to the Windsor Castle court, causing Caroline to uproot herself from the life she had established for herself in Bath to run his new household in Datchet. Once again unemployed, Caroline had little better to do in her new home than to scan the night sky with a refractor telescope William made for her, designed specifically to sweep the sky and find objects of interest. She found several nebulae previously discovered by Messier, and this was the first spark that fueled her future astronomical pursuits. She discovered one new nebula unknown to science, much to William's delight, despite his primary interest in finding comets. Nebulae were not well understood during this time, as they were simply believed to be clusters of stars too far away to be resolved. William believed establishing a large catalogue of nebulae may resolve the mysteries of these objects, and made an unfruitful attempt to do this himself during the summer of 1783. Upon employing Caroline's help for recording properties of his observations of nebulae, the two of them were very productive for the extent of the 1780s. The siblings moved twice more until they settled in Slough, where William worked for the most of the rest of his life. In contrast, Caroline's life faced great upheaval when William married the wealthy widow Mary Pitt in 1788. While William's marriage caused a rift in their harmonious household, Caroline made the most of the situation by pressuring William to request the king to give her a salary to operate William's recently developed 40-foot telescope in Slough. In this manner, Caroline became the first salaried woman astronomer known to history. By this time, William accomplished the primary purpose of his survey for nebulae. He concluded that some nebulae are indeed star clusters in disguise, while others are in fact self-luminous fluid. This allowed Caroline to move forward with her own career that she had slowly developed as a comet huntress. Comets were of particular interest during this time, since mathematicians computing their orbits required extensive measurements of their positions. By this time in the late 1780s, Caroline was acclaimed for her comet discoveries she made during times when William was preoccupied with other duties to the crown, such as a commission for 5 10-foot telescopes. By August of 1797, she had identified 8 comets. Caroline discovered her first comet in 1786 with her small Newtonian sweeper of 27 inches in focal length, and observed it from August 1st to November 12th of that year. Although she could not calculate its mathematical coordinates, she accompanied her observations with drawings. She was able to share with people as eminent as the Secretary of the Royal Society, who traveled to Slough for the exclusive purpose of viewing the comet through her telescope. Her next discovery was also with her small sweeper in 1788. Caroline's fourth discovery in 1790 marked the first she made with a new 5-foot sweeper that could sweep both vertically and horizontally. She discovered 2 comets this year and filled her observation book with complex calculations, exemplifying her development beyond just a record keeper. In this manner, she made significant discoveries all the way through 1797 until her personal life got in the way of her career as an observational astronomer. However, she still applied her skills to making major contributions to the field, such as a revised version of Flamsteed's star catalogue in 1798. She contributed an additional 561 stars Flamsteed had not included, and corrected many errors. Despite her many accomplishments, Caroline recounted the mortifications and disappointments which have attended her throughout a long life in her autobiography. Perhaps this was because of unfulfilling relationships with others in her life. Her dear brother William, whom she nearly worshipped, would command her on numerous occasions to move residences and take up certain observing programs as best served him, without much consideration for Caroline's own interests and desires or how it affected her career. However, she never lost interest in the discovery process of astronomy and always passed on her findings to experts like her brother and acquaintances she made through the Royal Society like Neville Maskelyne. While she did not have much interest in the process beyond discovery towards interpreting the physical phenomena she observed, her technical skills, such as her mathematics and the accuracy of her drawings, evolved with time. She actively performed follow-up observations, such as the depicted observation of the Great Comet of 1811 that captivated her and her brother. Heartbroken after William's passing in 1822, Caroline returned to Hanover, and her nephew John, the astronomy prodigy following in the footsteps of his father William, took over observing in Slough. Back in her birthplace, Caroline was a local celebrity, receiving a gold medal for scientific contribution from the King of Prussia, and the honor of being namesake of a crater on the moon and an asteroid. As beautifully written by one of her biographers, Caroline's career was rather like that of a comet. At first, her glory reflected that of her brother, as a comet reflects the light of the sun, but as she approached perihelion, she burned brightly not only with William's light, but also with the light of her own achievements. Further, like a comet in its orbit around the sun, her career blazed briefly, for only about 10 years. She continued to do desk work in Hanover, primarily assembling a nebula catalogue arranged in a format suitable for sweeping started by William and to be used by his son John. She was dedicated to her work until her gentle passing in her sleep in 1848. Caroline has left a strong legacy for future astronomers, women or otherwise. She was the first among the so-called women computers hired to work for the Royal Observatory in Greenwich, and long before the more famous Harvard computers. She is famously known for influencing Maria Mitchell's student, Margareta Palmer, who went a step further to compute the orbits of comets. While I cannot truthfully claim Herschel as this grand figure in my life who had always inspired me from a young age, I can say that I thoroughly enjoyed learning about her life and striking parallels with, as well as divergences from, my own. Her dedication to her family and loyalty to their academic interests, her early commitment to music. Fun coincidences like these caught my interest and made me think about how far we've come as a community. Women in astronomy are not as uncommon as they were, and I have been lucky to have never felt a sense of loneliness as a social outcast in my work. We have advanced in terms of knowledge and technology where we have the ability to make discoveries like Herschel's nearly autonomously with programs like OSU's very own Assassin Survey. Even Caroline's imperfections, such as her mistakes in comet identification, or even her sense of social unfulfillment, made her feel more tangible and relatable. She is a fascinating historical character whom I hope has rightfully escaped the shadow of her brother and established her own legacy with her own accomplishments and contributions to astronomy. Thank you. I'd like to welcome our next speaker, Allison Duck. Allison grew up on the rural and remote eastern shore of Maryland, where she could view the night sky as a child with little light pollution. Allison remembers coming home from swim team late at night in the dead of winter as a kid and seeing the clear, crisp sky dazzling with stars. Her wet hair would always be on the point of freezing, but she could not help but to brave the cold a little longer and continue to look up. After being exposed to such wondrous views of the stars, she could not help but want to study them. This childhood drive set her on a path to major in both physics and astronomy at the University of Maryland, College Park. At the University of Maryland, Allison began by volunteering at the observatory at UMD, home to a 14-inch reflector and 7 and 6-inch refractors. The moment she first held the keypad of the 14-inch reflecting telescope, her passion for astronomy solidified. It felt as if the entire universe was at her fingertips. She was looking back in time as she observed star clusters thousands of light years away. Looking through the eyepiece, Allison realized she had a live view of the past. It reminded her that the universe was dynamic even if her knowledge about this particular patch of sky was a few thousand years behind. Her love of astronomy allowed Allison to travel extensively to explore the field. More locally, she interned at the Johns Hopkins Applied Physics Lab and studied lunar regolith through observations collected by the Lunar Reconnaissance Orbiter camera. Globally, Allison was a summer student at the National Central University in Taiwan. She visited the 1-meter telescope at Lulin Observatory in Alishan, Taiwan. There she studied variable stars as observed by the Zwicky Transient Facility. Throughout her undergraduate career, Allison developed an interest in studying exoplanets, or planets around other stars. She completed an honors thesis looking at the effects of combining K2 and Spitzer space-based observations of exoplanets, and presented a poster at the American Astronomical Society meeting in Seattle. Her interest in exoplanets also brought her to the Ohio State University, where she is comparing the effects of different assumptions in stellar modeling on interpreting exoplanet transits with Dr. Scott Gowdy. Of course, Allison has interests outside of astronomy. She is placed in local air hockey tournaments and enjoys attending metal concerts.
Hi, I'm Allison Deck, and I would like to talk about an astronomer that inspired me, Dr. Nancy Grace Roman. As a brief introduction, Dr. Nancy Grace Roman is often called the mother of Hubble. She was an outspoken advocate for women in science. She was also NASA's first chief of astronomy. She was born on May 16, 1925, in Nashville, Tennessee. When talking about her love of astronomy, she says, "I always blame my mother. She showed me the constellations and aurora." While her father was a science teacher, her mother was a piano teacher. And while her father could answer her scientific questions, her mother was the one that really instilled the love of space. By 5th or 6th grade, she'd started in an astronomy club to study constellations, showing a penchant for organizing at an early age. By 7th grade, she knew she wanted to be an astronomer, even though it would mean another 12 years of school. In high school, when asking to take a 2nd semester of algebra instead of a 5th semester of Latin, her high school guidance teacher sneered and said, "What lady would take mathematics instead of Latin?" That really set the stage for a lot of the attitude that she would face trying to be a woman in science in the 1930s and 40s. Her high school career was also beset by a poor physics education from a befuddled business teacher who was roped into teaching physics that year. Also, her vision deteriorated, and her optometrist forbade her from reading outside of her school, which was a torture for her as she had been an avid reader. Instead, she learned to weave as a pastime and also took up knitting. She donated mittens to poor children throughout her life, as well as designed and sewed her own clothing. In undergraduate career, she attended Swarthmore University in Swarthmore, Pennsylvania. At the time, Johns Hopkins University only admitted for night school, even though Johns Hopkins would have been much closer to her family in Baltimore. At Swarthmore, the dean of women met with every incoming female freshman, and if she could not dissuade them from majoring in science or in engineering, she would never speak to them again, showing the amount of support of the administration at Swarthmore had for women in science at the time. Her first bit of encouragement, as she calls it, for being a woman in science came from one of her physics professors who said, "You know, I usually try to talk women out of going into physics, but maybe you might make it." Additionally, when one of her better professors left to support the World War II effort at Los Alamos, the replacement professor was senile, leaving her to study much on her own, as well as occasionally being the only student in astronomy, instilled strong values of having to work independently and not being supported throughout the field. In graduate school, unfortunately, this trend continued. She was a student at the University of Chicago and studied spectral classification and created a temperature of the brightness, distance, and stellar kinematics for many stars. However, she did not get much support from her advisor. In fact, there was a 6-month period where he would refuse to speak to her, even as they passed each other in the hallway. She then spent another 6 years working at Yerkes Observatory in Chicago, where she published the magnitudes and parallaxes for 600 high-velocity stars. She studied many stars with spectra similar to the Sun in one of her major discoveries. She divided the stars similar to the Sun in 2 groups based on line strength. Stars with stronger lines moved to the center of the Milky Way, much like the Sun. However, stars with weaker lines stretched farther from the path of the galaxy, indicating that they were older stars. These older stars produced the elements that allowed the younger stars to be more metal-rich. And she was one of the first to notice the difference in ages, even through these stars that had similar spectra. The image here is the spectra of the Sun for reference. The lines she was looking at were these dark gaps where metals and other elements were blocking the light of the stars. After at Yerkes, she slowly realized that she couldn't get tenure in academia as a woman. There were a few women in the field that did have tenure at the time, but there were very many senior women that didn't have tenure. Instead, she knew she had to change her course. So she worked at the Naval Research Laboratory as a general science advisor, eventually becoming head of microwave spectroscopy. Although even here, she was hired as a new PhD, despite having 6 years of work experience, because her salary at the observatory had been so low. Most of her work at Naval Research Lab, or NRL, was geodetic work, which studies the shape of the Earth using satellites, and conducting radar bounces off the moon. While they were doing the celestial mechanics work, scientists at NRL decided it might be good to have someone that knew something about astronomy around. However, she had limited room for growth unless she became an electrical engineer like many of her colleagues who were involved in making their own equipment and not just studying the data. She served as sort of as a jack of all trades. Shortly after arriving at NASA, an industry representative came to see her after a talk, and when he left, he said, "By the way, how long have you been in astronomy?" And she said, "All my life, why?" And he said, "Well, the last time I saw you was at a meeting on underwater sound." And she had been at a meeting for an underwater sound. The problems in propagation of underwater sound were not all that different from propagation of photons in stellar atmosphere, so she had relevant expertise. She was able to apply her expertise to many different fields throughout her career. She eventually arrived at NASA after working for NRL after a conversation in which James Clark, who had been at NRL, had asked her, "By the way, do you know anyone that would like to come and work for NASA and set up a program in space astronomy?" The idea of coming up with an absolutely clean slate to start up a program that would be likely to influence astronomy for the next 50 years was just a challenge she could not turn down. And that's all there is when asked how she joined NASA. And she was absolutely correct. The program she started at NASA did influence astronomy easily for the next 50 years, if not beyond. She joined NASA in 1959 when the agency was just 6 months old, laying the groundwork for all of the work it would later do. She described NASA's early rocket launches as babies learning how to walk. She said she was readily accepted as a scientist there, unlike in her previous institutions, although there were still relatively few women employed at NASA. The civil service had rewarded outside work, but only for men, but in 1960, President Kennedy gave Dr. Nancy Grace Roman the Women's Award for Outstanding Women in Civil Service. One of her first major programs was the Orbiting Astronomical Observatory, which was the launch of 4 such observatories. The first one, however, had a power failure shortly after launch. But the second one, she says, was a learning experience. We learned how to point a telescope at a single object and hold it there for a half hour or so. This makes the OIO-2 an ancestor of all tracking telescopes based in space, eventually including the Hubble. OIO-2 had 11 ultraviolet telescopes and had many scientific discoveries of its own, such as that comets had tails made of hydrogen and that novae increased in brightness in the UV, even as they faded in the optical wavelengths. However, the need for Hubble was clear. Lyman Switzer had done foundational work in the 40s supporting the need for a space-based telescope. The atmosphere of Earth just blocked too much of the light and made wavelengths such as ultraviolet nearly inaccessible. Initially, Hubble was proposed as a manned observatory. Aerospace companies were excited to get to work and didn't care much about what the design looked like. That's where Dr. Nancy Grace Roman came in. She said if aerospace companies were going to spend a lot of money building a telescope, they may as well design one that made sense. She says when asked about her major contributions to Hubble as a project that she provided perseverance and belief that it was possible. Largely, she worked with a group of astronomers to design a reasonable and useful proposal for Hubble. She was also the pen behind many congressional testimonies used to lobby for the creation of Hubble. Hubble itself had a bit of a rocky life. Early on, she was involved in lobbying efforts where she was the lead on discussing the science for the Space Telescope. while others handled engineering constraints as well as budget. However, she was still heavily involved with the Bureau of the Budget and other management agencies advocating for Hubble for every step of the way. Hubble was eventually canceled by Congress at one point, but fully got funded in 1977. However, the 80s were rife with engineering, leadership, and funding setbacks that delayed launch. Finally, Hubble was launched in 1990 with its first servicing mission to correct spherical operation in 1993. The legacy of Hubble is absolutely astounding, and it went on to touch nearly every branch of astronomy and revolutionize the field to what we see it as today. Now, when interviewed about her legacy, Nancy Grace Roman said that she was happy that women could get senior jobs. However, she noted that salaries still aren't equal, and she wants to see more women at higher ranks. When asked about her own impact on astronomy, she says that people aren't terribly interested in what gets things started. However, I respectfully disagree. Last year, she was recognized as one of LEGO's Women of NASA and clearly had a strong impact on the field that's being recognized later on. And personally, she's a hero of mine, and the reason I wanted to highlight her in this talk. I was fortunate enough to meet her a year before her death in December of 2017, and she's an absolutely incredible woman. She worked in every wavelength of astronomy, from her radar observations at NRL, her optical observations at graduate school, and then later the UV observations made by Hubble. She was truly a pioneer of women in leadership at NASA and truly paved the way for every young woman in astronomy that would come after her. Next, I do want to talk about one of those current day female astronomers, CAS's very own Ness Mayker. On January 28th of 1986, the Challenger was beginning its ill-fated space launch, and at the same time, a future astronomer was being born. The following afternoon, after a long, extended labor that stalled during the Challenger tragedy, Ness Mayker was born in London, Ohio. Despite this astronomical omen occurring during the time of her birth, Ness was not interested in planets or space. All she cared about was making stuff. Ness learned how to crochet from her mother when she was young. She brought her crocheting to the tiny church school she attended and raced through her problem sets as fast as she could so she could pick her yarn back up. Ness taught herself how to macrame a few years later and would sit under the trees at recess while her classmates played on the playground. Over the years, Ness worked odd jobs and took classes on and off at the community college. She stayed busy raising her son, Draylon, and continued to learn and practice new crafting techniques in her free time. In 2010, Ness met her partner, Rob Ebright, and in 2012, they received associate's degrees from Columbus State Community College. Around that time, Ness began apprenticing under Rob's mother, Jane Evans, a professional fiber artist who owns a sheep farm in Hopewell, Ohio. Jane taught Ness every step, processing wool from fleece to fabric. With the ability to create a wide variety of handicrafts, Ness started her own fiber art business. Ness loved her work as a fiber artist and looked forward to a lifelong career in the business of making things, until one day when she couldn't anymore. In 2013, Ness sustained an injury that would leave her unable to use her hands without pain or discomfort. Devastated by this, she reluctantly gave up her business. Limited by her disability and overflowing with free time, Ness spent many days in bed watching documentaries. When the documentaries ran out, Ness found a TV show called The Universe, which coupled beautiful imagery with astronomers talking about the cosmos. Knowing nothing about astronomy, Ness found this show to be educational and enjoyable. Her problems didn't feel so big anymore in the context of the vastness and complexity of space. She found a passion for astronomy and a new dream to one day become a research astronomer. Ness spent time over the next 2 years exploring the field of astronomy. She enrolled in every online course offered on Coursera, even taking some of them twice. She joined the Columbus Astronomical Society and began volunteering at Perkins. She bought a telescope and gave star tours to anyone who would listen. She followed every trail she could that would teach her something new about the mysteries of the universe. One day, Ness decided she couldn't go any farther as an astronomer without a university-level understanding of math and physics. After some motivating conversations within the CAS community, she enrolled at OSU to study astronomy professionally. During this time, Ness welcomed the addition of her daughter, Amelia, to her family. Ness graduated from OSU with a bachelor's degree in physics and astronomy in the spring of 2019. Ness's senior thesis research was on adapting a not commonly used method for measuring the temperatures of gas in star-forming regions in a nearby galaxy. This work was supervised by Professor Rick Pogge and postdoc Danielle Berg. Ness was accepted into Ohio State's PhD program in astronomy in 2019. Ness is now working with professors Adam Leroy and Laura Lopez, as well as postdoc Diaz Umoto, studying the properties of gas around recent supernovae and nearby galaxies to better understand how supernovae affect how efficient galaxies are at forming stars. One of Ness's favorite things about science is how there's never a shortage of things to learn. Oftentimes, answering one scientific inquiry will lead to many other questions. The field of astronomy has grown significantly over the last decade. Along with the increase in new astronomers, the field as a whole is becoming increasingly more diverse. Ness is looking forward to playing a role in the continuous scientific breakthroughs, as well as being part of an amazing community of people from many different walks of life that all share the same curiosity and the same passion for understanding the universe.
Hello, my name is Ness Mayker, and I'm going to tell the story of one of my favorite astronomers, Cecilia Payne Kokoschka. I remember the first time I heard her name and heard about her contribution to astronomy. I learned in class about a woman astronomer who had made a discovery so significant that its implications would fundamentally change the understanding of the composition of stars and ultimately the universe. She was all set to publish her results in her PhD thesis, except her advisor was so surprised by her findings that he dismissed them and pushed her to restate her analysis of her work, and reluctantly, she obliged. When I heard this, I felt sadness for what she had endured, her research disregarded and herself not being taken seriously as a scientist. This feeling resonated with me because at that time I was taking a physics class where my thoughts and opinions were frequently overlooked and undervalued by my male peers. I was upset to learn that a few years later, Cecilia Payne's advisor validated and published her results under his own name. Although he did give a citation for her work, he has been largely credited with her discovery. Unfortunately, this is not an isolated incident in the history of astronomy. Thankfully, Cecilia Payne persisted in her endeavors and is one of the more widely recognized and celebrated women in astronomy today. Cecilia Payne's dedication to her passion in the face of adversity is an inspirational tale that has encouraged women and girls around the world to pursue their love of science. Cecilia Helena Payne was born in Wendover, England on May 10, 1900. She was the oldest of 3 children. Her father, Edward John Payne, was a musician, author, Oxford University Fellow, and later in life he was a barrister and a judge. Her mother, Emma Lenora Helena Pertz, was a painter and a musician. At age 8, Cecilia decided to become a scientist after she recognized a plant that she had previously known only from her mother's description of it. She wrote in her autobiography, "The bee orchid was growing in the long grass of the orchard. An insect turned into a blossom nestled in a purple star. Instantly I knew it for what it was. I was dazzled by a flash of recognition. For the first time I knew the leaping of the heart, the sudden enlightenment that were to become my passion. I think my life as a scientist began at that moment. I must have been about 8 years old. More than 70 years have passed since then, and the long garnering and sifting has been spurred by the hope of such another revelation. I have not hoped in vain. These moments are rare, and they come without warning. They are the ineffable reward of him who scans the face of nature." At the age of 12, Cecilia was already profoundly accomplished. She had perfect pitch and was fluent in Latin, German, and French. She was interested in botany and could do algebra all the way up to quadratic equations. Cecilia Payne wanted to study botany and chemistry at the University of Cambridge. She could not afford to, but she earned a scholarship to cover her costs. She was inspired by Ernest Rutherford, who was running the Cavendish Laboratory, so she signed up for his physics course. This course inspired in her a love for the physical sciences. Cecilia Payne attended a lecture on general relativity given by Arthur Eddington. Afterwards, she described being almost driven to a nervous breakdown, thinking excitedly about its meaning, ramifications, and how it had changed her perception of the world. She decided then to change her major to physics, but spent more of her energy studying astronomy and working on research for Eddington himself. She completed her studies in Cambridge in 1923. But it wasn't until 24 years later, in 1947, that women were allowed to be awarded degrees at the University of Cambridge. Cecilia Payne wanted to earn a PhD and become an astronomer, but the only career option available to her was to be a teacher at an all-girls school. She decided to go to America to pursue her dream to become an astronomer. She received the Pickering Fellowship to study at Harvard via Radcliffe College, the women's college affiliated with Harvard University. The Harvard Observatory had been going through some radical changes prior to Cecilia Payne's arrival. The director of the observatory, Edward Pickering, had ramped up the observatory's use of astrophotography to capture the night sky onto photographic plates. Data was coming in faster than the men running the telescopes could process it. Pickering employed women to do the tedious work of classifying the stars on the photographic plates. Even though it was considered radical to employ women in the sciences at the university, these positions were considered clerical and worthy of a cheap and less educated workforce. Pickering hired more than 80 women computers during his time at the observatory, paying them less than half of what their male counterparts would have made. Regardless of the unequal pay and distribution of duties, this work was incredibly important. Their work built the observational foundation for the development of astronomical theory. Although the women had little ability to advance in their careers or to do theory work or even use the telescopes, they made huge contributions to the field of astronomy. One of these computers was Annie Jump Cannon. Annie devised a system for classifying stars that is still used today. She was not awarded astronomer status until 2 years before she retired, and although the International Astronomical Union adopted her classification system for stars, it was referred to as the Harvard system of spectral classification, rather than the Cannon system. Although the Harvard computers were not as appreciated or compensated as their work deserved, their contributions to the field of astronomy helped to push against the boundaries that kept women out of the field, and to begin to put some cracks in the glass ceiling that they found themselves up against. In the early 1900s, the composition of the sun and stars in general was not well understood. This image is a spectrum of our sun. The dark bands that you see are called absorption lines and are caused by specific wavelengths of light being absorbed by the gas in the cooler outer regions of the sun as the light is leaving the sun. The thick black line in the red section near the top is a hydrogen absorption line called H-alpha. The two lines in the orange-yellow region are called the sodium doublet, and the three wide green lines are called the magnesium triplet. Many of the blue lines and the other lines are from the presence of iron. Astronomers had recognized the chemical signatures of many of the elements that we know of on Earth that are visible in the solar spectrum. At the time, it was assumed that the sun was made up of the same elements in the same proportions as here on Earth. Soon after Cecilia Payne landed in America, she began her work at the Harvard Observatory, aiming to calculate the abundances of elements and stars. This image shows a sequence of stellar spectral types. On the left side of the plot, you can see the OBAFGKM sequence, which Annie Jump Cannon classified. Cecilia Payne demonstrated that the differences between the stellar spectra weren't caused by the star changing over time, but rather by the temperature or type of star they were looking at. Hotter stars had spectra like you see at the top of this diagram, so like the O and B stars. And cooler stars' spectra look like those on the bottom, it's like the K and M stars. Stars didn't change from one spectral type to another over the majority of their lives. Rather, there were different types of stars that were born into their specific category, which was a temperature sequence rather than an evolutionary one. Cecilia developed a way to quantify the intensity of absorption lines. Over the next year, she worked tirelessly analyzing the spectra of hundreds of stars, trying to turn her observations into a working theory. Because each spectral type was a different temperature, she realized that she could monitor the level of ionization of elements like silicon. In a cooler star, she would find the signature of neutral silicon, but a hotter star would have the presence of silicon which had been ionized, or in other words, had some of its electrons removed. This ionizing process requires hotter temperatures to take place. As the temperature of the stars increased, so did the amount of the ionization of the elements. From these observations, Cecilia Payne was able to tie together the intensities of the absorption lines with the temperatures of the stars, which she then used to calculate the abundances of the elements that make up the stars. So as I mentioned before, astronomers believe that the stars had similar compositions to our own Earth. Cecilia Payne discovered that the variations in stellar absorption lines was due to the differing amounts of ionization, not due to differing amounts of elements. The two key takeaways to her thesis research were that, regardless of spectral type, stars all had similar compositions, and this composition was made up of predominantly hydrogen. The abundances of hydrogen and helium in all stars were much greater than all the other elements combined, and they were very different from the composition of the Earth. She determined that hydrogen was the most abundant element in the universe. These results were groundbreaking because they went against the accepted wisdom of the time. Cecilia was discouraged from presenting her conclusion. Her advisor, Henry Norris Russell, was a very influential man in the field of astronomy. Cecilia feared that if she went against him, it would end her career. If he didn't approve of her work, it would not get published. Cecilia submitted her thesis, entitled Stellar Atmospheres, a contribution to the observational study of high temperature and the reversing layers of stars. In this thesis, she invested time refuting her result, describing it as spurious, instead of going into the implications of her discovery, which is what she felt compelled to do. Even though Cecilia Payne was made to hold back in her presentation of her discovery, her thesis was met with much celebration. It was referred to throughout the astronomical community as undoubtedly the most brilliant PhD thesis ever written in astronomy, and worthy of a place in every physical as in every astronomical library. Her supervisor, Harlow Shapley, had her thesis printed as a book called Stellar Atmospheres. Cecilia's advisor recommended her for a National Research Fellowship. Because Harvard did not award doctorates to women, Cecilia Payne was given a PhD from Radcliffe College, Harvard's sister college at the time. She became the first person to obtain a PhD in astronomy at Radcliffe Harvard in 1925. 4 years later, Henry Norris Russell validated Cecilia Payne's results. He published them, briefly acknowledging Payne's earlier work. Nevertheless, Russell was often given credit for her discovery. After her doctorate, Payne continued working at the Harvard Observatory, studying stars of high luminosity to understand the structure of the Milky Way. She then included variable stars to her sample and began surveying the Magellanic Clouds, two of the Milky Way's satellite galaxies. Her and her assistants made over 3 million observations. This work was used to understand the pathways of stellar evolution and was presented in Cecilia Payne's second and third books, Stars of High Luminosity in 1930 and Variable Stars and Galactic Structure in 1954. In 1932, Payne began a tour of Europe visiting observatories around the continent. While in Berlin, she met Sergei Kokoschka, a young Russian astronomer. She wanted to help him to get out of Nazi Germany. She found him a position at Harvard, and less than 2 years later, Sergei and Cecilia were married. Cecilia Payne Kokoschka continued working in her field as her and Sergei extended their family, breaking the stereotype that women were expected to give up their careers when married, and especially when with children. Cecilia was accused of scandalizing the astronomical community when she presented a paper to the American Astronomical Society when she was 5 months pregnant with her first child. A short while later, she left her second child with her husband to go lecture at the University of Chicago for 6 weeks. Cecilia and Sergei had 3 children and carried out their research together, with their observations on variable stars laying the groundwork for that field. Cecilia Payne Kokoschka writes in her autobiography, "A woman knows the frustration of belonging to a minority group. We may not actually be a minority, but we are certainly disadvantaged." She reflects, "As I look back, I ask myself what difference it has made to me as a scientist that I was born a woman. On the material side, being a woman has been a great disadvantage. It is a tale of low salary, lack of status, slow advancement, but I have reached a height that I should never in my wildest dreams have predicted 50 years ago. It has been a case of survival, not of the fittest, but of the most doggedly persistent. I was not consciously aiming at the point I finally reached. I simply went on plodding, rewarded by the beauty of the scenery, towards an unexpected goal." Cecilia Payne spent her entire career at Harvard, yet was not given the title of astronomer until 1938. 13 years after her widely celebrated thesis work. Although she had been teaching a full course load, she was not given the title of professor until 1956, when she was given a matching salary and promoted to chair of the astronomy department at Harvard. This marked the first time a woman was made either professor or chair of a department at Harvard. During Cecilia Payne Kokoschka's career, she published over 150 papers and several monographs. She also published 4 books on stars and stellar evolution in the 1950s. She became emeritus professor of Harvard University after retiring in 1966. She continued to write and conduct research until her death in 1979. Cecilia followed her passion for science, encountering resistance and discrimination along the way. Her official placement into the astronomical community dramatically changed the field of astronomy for women, helping to open the doors to a more diverse future in the sciences. She became a role model for many. I want to close with the following quote from her biography. Young people, especially young women, often ask me for advice. Here it is. Do not undertake a scientific career in the quest of fame or money. There are easier and better ways to reach them. Undertake it only if nothing else will satisfy you. For nothing else is probably what you will receive. Your reward will be the widening of the horizon as you climb, and if you achieve that reward, you will ask no other. Thank you. Kirstin Bully is originally from Rome, Georgia. A large part of why she became an astronomer is because of the military and the amazing opportunities she had to do research. Growing up, she was always curious and always wanted to know the why behind everything. After taking her first physics class, she knew that she wanted to be a scientist or an engineer. Coming from a poor family, they were not financially able to support her through college, so she chose to join the Army in order to pay for her undergraduate degree. By joining the Army, she was able to do an internship at Lawrence Livermore National Laboratory through their ROTC program. There, she worked with an astronomer on high redshift galaxy detection, and she absolutely loved it. After graduating from Georgia Tech with a bachelor's in physics, she began doing exoplanet research with Ji Wang at OSU. She's particularly interested in the geophysics of exoplanets, as well as habitability. Kirstin wants to help answer the question, are we alone? Currently, her research looks at the planets around halo stars, or stars that orbit the outer regions of their host galaxy, to see if planets can form around stars that contain little amounts of iron. One upcoming NASA mission that she is very interested in is called Dragonfly. This is the mission that's pictured in this slide. It is a mission to Titan, the largest moon of Saturn. Dragonfly will look at the chemical processes to see if there may be life on Titan. Although Kirstin is interested in exoplanets and habitability, Cecilia Payne Kokoschka is one of her favorite female astronomers. She was inspired by how Cecilia Payne was bold enough to propose her research, even though it contradicted the science at the time. Kirstin is also inspired by Caroline Herschel, the astronomer on the right. Caroline is a planetary scientist who is an expert on planetary rings and has studied the moons of our solar system, such as Saturn's tiny ice moon, Enceladus. Caroline Herschel also was a part of the imaging team for Voyager missions, and she led the imaging science team on the Cassini mission. When Kirstin isn't thinking about planets in space, she loves to explore and do new things. Some of her favorite things to do are travel, hike, snowboard, and scuba dive. Kirstin wanted to present with us today, but she is currently away taking the basic officer leadership course for medical officers. Kirstin is in the United States Army Reserve and is training to be a medical evacuation platoon leader alongside her work as an astronomer.
All right, thank you everybody. That wraps up all of our presentations. I'm going to leave the stream going for a little while, and I'm going to play a video from NASA about women in astronomy. It's a couple of minutes long, and it gives everybody a chance to chat with the speakers or do any closing comments in the chat before I end the live stream. Thank you so much for coming. This was a really fun event to put together, and I really appreciate everybody who came. Thank you.
So 1992, first meeting, first of all, we had to persuade people that there was a problem. They weren't sure there was any reason women weren't in astronomy. They thought, well, it's just because they don't want to be in astronomy.
And so I think we went to the meeting not knowing a lot about the history of women in science. And what I remember is learning the history of women.
The interesting thing was that the first meeting was almost 20 years ago, and we've seen a drastic change in the field in those 20 years, in that there is a much higher percentage of women coming out with PhDs now in astronomy and physics.
I look at planetary analogs, and I try and understand the the microorganisms that live in those materials and how they have adapted.
I study how stars move in galaxies.
And I actually work on black holes, supermassive black holes.
I'm particularly interested in the environment of active galactic nuclei. These are the bright centers of galaxies.
As a scholarly student, but that sense of self-confidence that comes from being in a place that supports you and says, you're brilliant, you can do it. I have been so impressed too.
This one is very different because now everybody knows the history of women. Everybody that's at the meeting knows the history. And so they're much more subtle questions.
And they really wanted to open it up to be a discussion of diversity in astronomy, and so to not just focus only on women in astronomy, but to focus on underrepresented minorities and also the numbers of, or the generations that are now in the workforce in astronomy.
If you have the diversity around you, it has no impact on the work that you're doing. This is a professional environment, and it doesn't matter if you're black or white, a woman or a male, from one country or another, it doesn't matter. The goal is to get a job done, to learn something.
When are we done? When are we done? We're done when the demographics of the profession are the same as the demographics of the society we come from.